In this lesson, we're going to learn one more way to find the volume of a solid of revolution. This is called the shell method. So if we have a solid, here's an example over here, nice GeoGebra. If we take a function like x times the sine of x, that's this little green curve here, and we're going from 0 to 3.2, all right? So 0 to 3.2 means, well, let's see if we can get this to move. There we go. Okay, so 0 being the middle of that little donut-looking thing, and 3.2 would be the outside, all right? So there it goes. All right. So we're going to rotate this around the y-axis. Now, this gets a little challenging when we're talking about the washer method in some cases. So we need another way. And what we're going to do is we're going to think about this not filled with discs or washers, but we're going to fill it with these rings, all right? These cylinder rings that are the lateral face or the vertical face of a cylinder. So here we've got one paper-thin ring that kind of fills up some of that area. And as we get more and more, we can fill the area up. As you can see, kind of filling up that donut kind of looking thing, kind of a bundt cake or something like that, huh? And we fill it up. So if we have more and more rings, then eventually when we have infinite rings, we fill it up and we have complete volume. Now, the question is, how do we find the area of these rings? Because these are infinitely thin rings, and so same kind of concept as the discs. If I can find the area of one of these rings in terms of x, then we can find the volume of this, all right? So that's the idea of the shell method, okay? So looking at one, here's one that we're revolving around the x-axis. So instead of talking about washers or discs, we're going to think about this ring here, all right, or this shell, okay? And so this shell right here is the outside of, let me go like this, of a cylinder. Okay, and so if we take this cylinder and we just want to talk about the outside of the cylinder, not worried about the circles on the end. There are no circles there. These are hollow. So if we think of this as like a soup can, so think of this soup can and think about the label. If we peel this label off, we're going to get a rectangle like this here. All right, and so this rectangle would wrap around this here, all right? So the lateral surface area is what we call this. We call this the lateral surface area. And this lateral surface area comes from the height. So this is the height here. And all right, let's put the height is that distance there. And then this distance right here, this length of this rectangle is the circumference, because it's got to wrap all the way around that can, right? So this is the circumference, which is 2 pi r. Circumference of a circle is 2 pi r, all right? So each of these rings that we're going to have is going to be have the area here, and that is the 2 pi r, which is circumference, times the height. That's the length times the width of this rectangle, okay? So we're going to use this idea to come up with an expression for all these rings that build up to make the solid. Okay. So let's go look at an example, and it'll make more sense as we do that, all right? So we're going to have two situations. One situation where we're going to have a vertical reference line here, and then we're going to have one where we're going to have a horizontal reference line. All right? So here we have a solid. It's bounded by the function y equals x minus x cubed. That's this black line. And between that and the y-axis, we're going to rotate this around the y-axis. Okay, so it's going to come around and around. Okay, so get kind of these wings like this, I guess. Okay, so if we rotate this around, we're going to get this shape. Okay, it's going to kind of be this mounded circle kind of deal. All right. So that's what's going on when we rotate around the y-axis. But we just want to focus on this rectangle, or really just a line. Because when this rectangle gets infinitely thin, it just becomes a little line segment. And as this rotates around the axis, that blue line there, it's going to make this cylinder, this lateral surface of a cylinder. And so this just represents the path of one line that goes through here. Okay? And so we need to find the area of this surface here. Again, it's just the lateral face of a cylinder. So we remember the lateral area of a cylinder, we just found out, is 2 pi r h. So keep that in mind. So we got to figure out what's the radius here and what's the height. So the area of that strip there, or that shell, would be 2 times pi times the radius. Well, what's the radius? Well, where is this line that we've kind of randomly picked? Well, it's at some x value. So we've traveled out some x value, and that is the radius. Okay, or what the book here is calling p of x. Okay, so the radius is x. Well, what's the height of this ring here, or this shell? Well, the height is determined by this function x minus x cubed. All right, so the height is the function, which is x minus x cubed. So we can put that in place of height. And there's our area function. Then we take the power of calculus and we're going to integrate it. 2 pi x times x minus x cubed dx. And that the x value is going from 0 to 1. So this shaded region, in that shaded region, the smallest x value is 0, the largest is 1. And we'll usually take this 2 pi outside. And we've got the integral. This is an easy one to do by hand. X squared minus x to the fourth when you distribute that. And this is from 0 to 1. But we'll go ahead and, now that I said it's not too bad, it's going to get some ugly fractions and stuff. So let's just go ahead and get our calculator on this. And the calculator is going to give us 4 pi over 15, which is approximately 0.838. That's the idea there. Okay. So now notice, by the way, that this reference line here was parallel to the axis of revolution. That's opposite from the disk method or the washer method. So here we want to find the volume of this revolution here using the shell method. All right, so we're going to rotate now about the x-axis here. So we're going to take this shape, rotate it, and, well, we're going to get this solid kind of looking thing here, kind of a bell shape, a sideways bell shape. So let's think about the path of a reference line here. Okay, now this is the function x equals e to the negative y squared. Notice that it's solved as a function of y, x as a function of y. All right, so this line here has a certain y value, a certain height, and we're going to rotate it around here. and it's going to make this cylinder when that rotates, that particular line. So when that line rotates, it gets a cylinder, so we know the lateral area of a cylinder is 2 pi r/h. So the radius of this, well, the radius is this distance right here now, and that is the y value. So we have 2 pi times the y value. And the circumference of this, well, that depends. That depends on this distance here. I'm sorry, not the circumference. I said that wrong. The height. That is the height. The height of a cylinder goes as the distance between the two circles. So the height, that distance there, is our function, e to the negative y squared. There you have it. That is one ring, so we're going to add up all the rings. So 2 pi, we'll go ahead and move the 2 pi outside. Y times e to the negative y squared, dy. And we have to look, the smallest y value is 0. The largest y value is 1. So we're differentiating with respect to y here. Okay, there you have it. Again, notice that this line of this reference line is parallel to the line of revolution there, or the axis of revolution. So using the calculator, we get approximately 1.986. Remember to round to 3 decimal places there. So that's the idea. It's all about cylinders, and specifically the lateral surface of a cylinder. And we find the area using lateral area equals 2 pi r/h. Then we use integration to add up all the areas, and that gives us our final answer. So to wrap this up, we now have several methods. We've got the washer, the disc method, and the shell method. Now the washer and the disc often are considered the same because they're the same idea. Okay, so the difference here is when we want to use the disc method. So here we're using the disc method. Okay, the disc method always uses a representative rectangle or line that is perpendicular. Okay, so here we're talking about this line right here that is going to rotate around the y-axis, giving us a disc or a washer. Okay, here, disc method, we're taking this line and we're rotating it around the y-axis there, or x-axis. Okay, but when we're talking about the shell method is going to be reversed there. We're going to be, the line that we choose or the rectangle that we choose is going to be parallel to the line of revolution. So if we're going around the x-axis, we're going to be talking about a horizontal reference line here. Something like that. That's a pretty sad cylinder. But that's the idea. So parallel for the shell method, perpendicular reference line or reference rectangle for the disc method.